Hey everyone, hope you're enjoying your E-Day today. Our event is Tinkering with Circuits. My name is Gary Lopez. I'm a master's student in Biosystems and Ag Engineering.
And hi, everyone. My name is Carla. I'm also a graduate student in Biosystems and Ag Engineering, and I'm working on my PhD. Thanks for joining us today. We are very excited to show you guys how you can get started with designing your own projects at home right from your computer. Now, before we start, if you get a little lost or overwhelmed, feel free to pause the video and also check out the links in the description below that have the updated project for the start of each segment today. If you click on it, you'll be right up to speed to follow along again. So I'll hand things over to Gary and we can just jump right into it.
So hopefully by now you guys have made a Tinkercad account. If you haven't, go ahead and do so. It's free with Google. This is what the home screen will look like. And you'll see over here on the left-hand side underneath 3D designs, there's circuits. So if you go over there and click on circuits, it's going to open up a new page. And this is where you have all your previous projects. Go ahead and click create new circuit. Now it's going to open up a new workspace. Once that loads up, you'll see over here on the right hand side, there's a list of components. You can scroll down to see more. And then if you click the button there, it gives you a brief description of the components that they have there. So let's go ahead and let's make our first circuit. We're going to drag out an LED. So put that over here in the workspace, just anywhere. I'm going to pull out a resistor and also a 9-volt battery. So to wire this up, we're going to go from the positive, the red terminal, to the bent leg of our LED. And then we're from the other leg of the LED, we're going to put that to one end of the resistor. And I'm going to hit start simulation up here on the top right. We see nothing happens. Nothing occurred because we have an open circuit. So in order to allow everything to flow, the electricity to flow, we need to close it. And you see the light is turned on. So congratulations, we made our first circuit of the day. So to further build things, we're going to drag out a breadboard. And you'll see that as I put my mouse over certain sections, that the things that highlight in green mean they're all connected. So I plug one in here, I can plug in down the line there. Those are connected that way, and these go up and down. The other device we're going to need to introduce is an Arduino. This is a microcontroller, and we'll see here at the bottom we have different voltage pins, some ground pins, analog and digital pins. But like the brains of this operation is this chip here. This allows us to control things as inputs and outputs, and it allows us just to do more than just, it allows us to actually do some cool things and power and control certain devices. Now, these are actually physical components, and this is what they look like in real life. So that's a breadboard, and that's an Arduino. Carla?
And so now we can actually build our LED circuit using an Arduino. So let's take that LED, place it on the breadboard, and we'll connect our 5 volts of power from the Arduino to the positive rail all along here. And then we'll connect ground from the Arduino to the negative rail. We'll then need to close our circuit like we did earlier with Gary by connecting positive to positive, so power to the anode, which was this little leg sticking out, and then negative to negative, so ground to cathode. Now let's try it out. Press start and so this star is telling us something is wrong. There is too much electric flow going through the LED and it just doesn't like that. So we need to decrease the electric flow. And so how do we do that? Well, we can use a resistor like we had earlier because its job is to resist electric flow. So let's stop our simulation and let's bring out a resistor, the same one that we had before. And so this will just help make sure that we don't accidentally damage or break any parts in real life. So click and press delete to get rid of this. And we'll connect it on the cathode side, the negative side, right there. And we'll close our circuit. And when we try it again with our simulation, let's see what it does. Press start and it works. But here's the thing. With an Arduino, we can do so much more than just turn an LED on or off. So let's stop our simulation and change this connection on the anode, the positive side. So right there, click and delete, and we'll connect pin 4 to the LED right there. And so let's press start again, and let's see what happens. Nothing. So why is that? Well, we're not really telling it to do anything. We haven't written any code. So let's open up the code panel. And let's drag this over to the garbage. We don't need it. It's just an old example. And we can start off programming by dragging this coding block over. So since the LED that we just connected to was in pin 4, we'll choose that and select high, which is telling the LED to turn on. You choose low if you want to turn it off. So press high, and then let's try it out, press start, and the LED turns on now, no problem. But to see what the actual code behind this looks like, then let's select the blocks plus text option. And so this is the program that we used just now to turn on the LED, what we did in blocks just now. And this is what the code would be if we actually wrote it out. So we told it where the LED was connected to, pin number 4, and we said turn it on high instead of low to turn on the LED using the command digital write. But this was a pretty simple program, so let's make things a little bit more interesting. Our LED could only turn on and off, and it's always the color red. So let's use an RGB LED to make a custom color. So let's type in RGB, drag this little guy over with the 4 legs onto the breadboard, and like with the previous circuit that we did, let's also use a resistor. So let's find that and drag it over. And like with any RGB LED, we can control the levels of red, blue, and green to the mix to mix any color that we want. So let's connect the resistor to the cathode again, the negative side, and make a connection to ground. So drag it over right there to the Arduino. And then we're going to connect the red leg to pin 11 with the little squiggly in front. And this just means that instead of sending a signal that's just on or off, we can send a signal that's in between. And this is by using PWM, pulse width modulation. And this is just how we can control the levels of red that we use. So again, let's connect that to pin 11. And also just to make it easier to see what we're doing, let's change the wire color. So let's change it to red. And then we're also going to do the same thing for the blue leg. So we'll connect it to pin number 10. Let's drag that over. And let's also change the wire color to blue. There we go. And then we'll finish off by connecting the green leg to pin number 9. And then we can just leave the same color. Now let's go to the code and add on to it. So let's drag over this last block. And here we can select the pins that we just connected the red, green, and blue LED legs to. And so those are the numbers 11, 9, and 10. Make sure that it's in that order of RGB. And for the color that we want, let's choose something cyan or turquoise like this one. And now let's try it out. Press start. And there we go, our custom LED color. And now I'll let Gary explain some of the coding behind what we just did. And just so you know, this is checkpoint 2.
So looking at the code, you see that we have the digital write, which Carla explained is simply high or low signals. But we also have an analog write. That can vary between 0 and 255, with 0 being low and 255 being high. The way this works, the pulse modulated width, it's a ratio of on and off signals that gives us these intermediate values, these in-between values. So it's kind of like if you want warm water at your house, there is no warm water tap, right? You have to typically put on the cold, put on some hot, and then you get something in the middle. So, we want that cyan color. You see that blue and green are high and red is fairly low. It's at 51. And this is, the way with light when you mix certain colors, how you get, the in-between colors. So we're going to pull up a color wheel here in a second, take a look at this to kind of explore a little color theory. But again, pay attention that blue and green are high and that the red is at a value of 51, which is like 20% of what it could be. So up here, we're going to go to the color wheel to look at it. We see that for cyan, it's a lot of blue, a lot of green, and if we go maybe towards one of the little corners there, has some red. So that's what we have. But what happens if I was to pick something that was like more purely red? What would we anticipate the blue and green happening? So one down to the bottom. Let me drag that up, and I'm going to pick something that's looks like pure red. So when I do that, you'll see that I actually picked pure red because red's at all the way up to 255 and the other ones are at 0. So for a pure red signal, you don't need any blue or green to do so. We're going to add another component to our project right now. So go ahead and click the code to close that window to allow you to have more workspace. And in the search bar, I'm going to type in just photo. That's enough to get the photo resistor. That's the thing right here that has this little squiggly line back and forth. Click it and drag it onto your breadboard. And then we're going to connect one leg from the positive there to the leg on the left. And then I'm also going to need to grab a resistor. So I'm going to drag that. I'm going to put it over the middle junction there to jump that. And I'm going to change the resistance to 10 kilo ohms. The K stands for kilo. The little horseshoe stands for ohms. Connect the bottom lat to the negative terminal. And we're going to take a signal from this. So I'm going to put a wire between the resistor and the photoresistor. And I'm going to connect that down here to A4. And to make this wire stand out, I'm going to make it orange for you. Okay, so once we do that, we can hit, code because we need to actually tell the computer what we're doing. Now, I'm going to click here. I'm going to go straight to text. The reason I'm doing this is it allows us to have more control. Go ahead and press continue on this. This is what I would call hard coding. You're actually physically putting in the things there rather than using like the blocks as an intermediate, which is a great way to learn though. So I'm going to start it out with int, and I'm going to put light val with the capital V for val, semicolon. You have to make sure you end it with a semicolon, otherwise it's not going to work. And then I'm going to press enter, then int. So these are just storing these as values. I'm going to put light pin with the capital P equal to A4, and that's with the capital A, semicolon, and then int, press enter, and then int. Then I'm going to put a space dt equals 1000. This is a time delay. The 1000 is in milliseconds. There's 1000 milliseconds in every second. So we're going to put a 1 second delay in our program. Go to the last pin mode, press enter once or twice, give you some working space. And we're going to put serial.begin with the capital S. We're going to put in parentheses 9600. This establishes the communication between our board and our computer. We're going to put a semicolon, and then we have to put the pin in there. So we're going to put pin mode with the capital M on mode. And we're going to put in parentheses, we're going to, we have to put the pin location. So we're going to put light pin because that's equal to A4. And then this is going to be an input. So if you look above, everything else is output. So this is an input. So we're receiving a signal rather than sending one. Close the parentheses, make sure you put your semicolon. And then after the last analog write in the void loop, go ahead and press enter twice, once or twice to give yourself a new line to code on. And we're going to put light val. You have to spell it the same way as you did above. So if you spelled it differently, if you have it all in lowercase, do so. It is case sensitive. It will not work if you don't do that. And put equals analog read with the capital R on read. And in parentheses, we're going to put light pin. And again, you have to spell it as you did above. Go ahead and close that and close parentheses, put a semicolon, press enter. And we're going to want to be able to read this or view it. So we're going to put serial with the capital S dot print. And in parentheses, we're going to put quote light value. So again, quote. So you want to get that in there. And then this part, you can spell it any way you want. There's just going to be like a label. So light val, then I'm going to put the equal symbol, close quote, close the parenthesis, and put a semicolon. And then I'm going to press enter, and then I'm going to put another line saying serial dot print. So, put an L dot print. And then I'm going to put LN following that. That's going to skip a line in the display. Put our parenthesis, put light val in there, close the parenthesis and semicolon. And the last thing we're going to do for this section is go to the delay, delete the 10, and we're going to put our DT in there. Once you've done that, you finish the code for the section. So go ahead and hit start simulation, and nothing happened. Well, actually, it's working. We just got to click on our photoresistor and use the slider to simulate dark to light. To see the values, we click here at the bottom, serial monitor, And we see, initially we had something down in the 50s, 400s, 900s. As we move the slider, we're going to get different values. Carla's going to show you how to take these values and calibrate another device using them. And this is what it would physically look like. At this point, we've reached checkpoint 3. So if you're lost, you can go ahead and pause or launch the checkpoint. So here will be a quick image of what it looks like, and I'll hand it to Carla.
So we're now going to add some cool gadgets to use with our photoresistor. But first, we need to write down some important numbers. So let's press start our simulation again. And from this data stream, we have to see what the high and low values are. And these are just going to be our endpoints, so what we're working within. They don't have to be exact, just something close to it. And it's okay if yours is a little bit different. But here, when it's dark, our low value is about 733. And when it's bright, our high value is about 964. Now let's put that to the side for a moment and stop the simulation. And let's look up another part that will take our project to the next level. So let's search up the servo motor, also just known as a servo. And basically, it's just a little motor where you can set its position, so you can move it around. And in this one, the little white arm moves between 0 and 180 degrees. And they're pretty popular for a lot of applications. You can find them in systems like robots. So learning to use them now could be pretty useful for future projects. And today we'll be using it with our photoresistor. So depending on how light or dark it is, we can move our servo to a certain position. So to start off, we'll connect the negative to negative, so ground to ground right there. And we'll connect positive to positive, so power to power. So click right there, and then power to power. And then let's also change the color for that. So let's go with the red. And then lastly, let's connect our signal from the servo to the pin number 3, again with a little PWM squiggly right there. And then let's change the color once more. Let's go with purple. There we go. And so to make it work with our system, we'll have to add in a few lines of code. So the first thing we'll do is make some room and then go back to the top and write out a hashtag, the word include, space, and then the library name, which in this case is servo.h with a capital S in between little triangular brackets. No semicolon this time. And this is just basically telling our program to include or download the library that has the servo commands that we'll actually be using. Now let's move down here and we're going to tell the Arduino what the name of our servo is so that we can actually tell it what to do later on. And so we'll write out the line, servo space servo1, semicolon, capital S. And then we're going to create a float variable, which is just a place to hold our decimal numbers for the angle of our motor arm. And then create an integer that holds the number of the pin, which in this case is a number 3. That's what we connected the servo to. And then further down, we'll also create another float variable, so a placeholder for the slope, which we'll talk about in a second, but essentially it's how we're going to calculate the angle of our motor arm, so how much we're going to move, based on the photoresistor values that we have earlier from our sensor. And then below that, we're also going to add in a float variable for the high photoresistor value. Which in this case, mine was equal to 964. It's like yours might be a little bit different, 964. And then below that, we're going to add in a float variable for the low photoresistor value, which was equal to 733. Like again, yours could be a little bit different. That's not an issue. And then let's make a little bit more space and add in 2 more float variables. So one for the maximum angle of our motor arm, which in this case was 180, and one for the minimum angle, which is 0. And now all of these variable lines should have semicolons. So all of them except for that very first line that we typed out. And just make sure that your capitalizations are consistent throughout. So here we capitalized min, and make sure to do that further down. And so we've done with those variables. And so we'll move down here and make some room. And here we're going to write out the line pin mode with a capital M, parentheses, servo pin with capital P. And this is just the variable that we created with our pin connection, and then comma output, close parentheses, semicolon. And then the next line, we're going to type out servo.attach, and then inside of parentheses, the variable servo pin with a capital P. And then remember your semicolon, and that's just letting the program know that we connected our servo to pin number 3. Perfect. So then further down our program, we're going to add in a few lines to calculate the slope that I mentioned earlier. And so let's delete that ln, and then right after that, let's add in some space, and then for the variable slope that we're going to be using the formula, the point slope form. And so here we're going to take the difference, so subtract the minimum and maximum angle values, which in this case are 0 and 180, divided by the difference between the high and low photoresistor values that we recorded earlier. And so if you have no idea what point slope form is, don't worry about it. You'll learn it in algebra. It's like, but for now, just trust that this is what needs to happen. But if you want more of an explanation, you can definitely contact us about it. Now from this, we can calculate our motor arm angle by taking the slope times our light val with a capital V minus slope times high. And then remember your semicolon. And the idea is that when it is dark, the arm points to the left, and when it's bright, it goes to the right. And so now that we have our angle based on the photoresistor value, we can tell our servo motor, which we called servo 1, to go to this specific angle. And so we'll write out servo.right, and then parentheses angle, and remember your semicolons. And then moving further down, we're also going to add in a line, serial.print, capital S, and then inside of parentheses, put in your quotation marks with angle equals, and then close that out and add your semicolon. And then below that, add an additional line, serial.println, and then inside your parentheses, the variable angle, semicolon. And so this is so we can see the angle as it changes in the serial monitor. And so that's all the code we're going to write. I know it's quite a bit. So let's try that out, and ta-da, it works as expected. So as it gets dark, it goes to the left, and when it gets bright, it goes to the right. And so we can see here the light values from earlier, along with the motor arm angle that we calculated from that. So now Gary is going to show you what you can do with this and what this actually looks like in real life. And just so you know, this is checkpoint 4.
So to download our code, you hit the code and you hit this little arrow down. Now Tinkercad likes giving these weird names to your code as a default. So I'm just going to go ahead and just press open with. Okay. Arduino is a free open source software, so you can just Google it and find it to download it onto your computer. When this pops up, you're going to want to press OK. And I'm going to make this full screen for us. So this is our code that we just made over in Tinkercad. I'm going to press that check mark, and you'll notice on the right-hand side towards the bottom, there's a little status bar loading up. And once that goes all the way over, we know our code's good. And now we have to send it over to our board. So I'm going to go to Tools, Board, and I wanted to go to an Uno. That's the type that we modeled it on. And then Tools, and I'm looking at the port now. And we'll see that right now I just plugged it in, so it's not viewing it. Sometimes it takes it a couple seconds for it to kind of sync up and link up. So again, port, it's still not showing any the connection I want. So I'm just going to click out, and hopefully this next time it's there. So click out, go to Tools, and we see it's there, Arduino Uno, and we have the check mark, so we're good. So go ahead and click out, and then I'm going to press the arrow that goes over to upload it to the board. So now it's sending the code from the computer to the board. Again, there's a status bar on the bottom right-hand side, and once it goes over, it's now our device is actually working. To see the output from it, we're going to go to serial monitor, and these are actually the values that it's sending over. So we have a angle value and a light value. So you see I'm getting values right now about around 900. That's when I was on a high. I was shading with my hand. I'm getting something mid 500s. And when I go to completely cover it, I'm getting around 110, 115. And I release my hand from it. Now we're back at high. So now I'm going to calibrate my particular setup because it's acting different than the model we built in Tinkercad. To do so, I'm going to click out. I'm going to go to the low value. I'm going to change that to 115. And I'm going to change the high to 900. And the servo I'm working for only has a 160-degree working range, so I'm going to change that from 180 to 160, and I'm going to send the code over. And now I'm going to show you what this device actually looks like if you were to, build it. And I put a little thing on there to show the dark to light and how it can point and indicate that. Now, this would be an example of what you could potentially do if you're controlling a greenhouse, if you wanted to regulate how much light's coming in, um, or something to that matter, or control some solar arrays. So you see it when I go to completely cover it, it goes all the way to dark. At this point, Carla's going to jump in and tell you about some of the research that's actually happening with her project here at UK.
So keeping what we've covered in mind, all of these ideas and basic principles of prototyping and designing circuits, that can all be found in the foundations of the projects and the research that we do here at UK in the Biosystems department. It might look a little bit different. We use different programs and parts. The projects are bigger, but the same ideas are still there. So as an example, right now we're working on a project where we're using sensors to collect GPS location and weather data from a drone so that we can use that data to make better predictions about the environment around us. So why is this important? Well, if some sort of contaminant is unexpectedly released into the air, either because of an emergency situation like a forest fire, an oil spill, or maybe even a nuclear disaster, we want to be able to understand how weather affects the way a contaminant moves around and how it spreads, which can be really important when making a plan on how to keep people safe. And so when we look at the weather side of the project, the prototyping also started out with designing our circuit on the computer. In this case, it was a bit more complex. We had more parts going on and multiple sensors. So here we had some for pressure, humidity, temperature, a microcontroller, which is like a little computer, along with a bunch of other things. But it's an important step to do where you can plan out the connections between parts and make sure that you're not overlooking anything too important. And so after this, a PCB or printed circuit board is the next step for prototyping, because here we're planning out where parts physically go. It keeps the connections from before, and when you're ready, it's what you send to a company so they can actually physically print it out for you. And so on top of this, you can also make a nice 3D model of your design. And this way you can design additional parts that you want to 3D print and see how they fit together. Just like we did with this base, where we can snap in the board to be able to connect it to the computer for programming later on. But once you send it off to get made, a few weeks later, you actually have in your hands what you designed on the computer. Since this is an ongoing project for us, the next step would be to solder or attach all the different sensors and parts onto the board by hand so that it looks something like this. And then we'll test it out to see if everything works the way it should before taking it out into the field. But switching over to the GPS location side of the project now, this may look a little bit more familiar. So in our prototype, we're using a Raspberry Pi, which is kind of similar to the Arduino that we use today. And so here we have our own LED to help tell us what's going on with the program, a push button to start and stop programs, and then also our set of GPS devices, which help us get the drone's location within a couple of centimeters. And that whole system goes on the drone and it attaches by that blue mounting device, which was 3D printed in our labs. And so we had to make a 3D model of it on our computer first. And this just goes to show that if you can design it, you can really create just about anything. And once you have a system that's ready to be tested, then it's go time. Here you can see a little bit of that blue of the mounting device from earlier. And using all of this together, we're able to collect large amounts of data using a program we created. And so coding is a very useful skill to have. Our program is writing down about 9 lines of data per second for each device. And so this is way more than we'd ever be able to do by hand. But to recap, similar to the way that we collected data from a photoresistor sensor to control a servo motor to potentially move plants around in a greenhouse, we're wanting to use weather and location data collected from sensors on a drone to better respond to airborne emergency situations. But this is just one project of the many, many cool ones that we're doing here. And depending on your interests, there is definitely something for everyone in biosystems. And with that, I'll hand things over to Gary so he can wrap things up for us.
So thank you guys for participating in our event today. Below in the description there should be a link to a survey. If you could take that back, we'd appreciate any feedback you'd give us. Also, there's a link to a Google Doc that has all sorts of information if you want to buy your own circuit kit to start playing around at home, or if you can continue your Tinkercad journey. There's some tips and tricks on there as well. Also, recommended YouTube channel for you guys to look at. If you have any additional questions for us, you can reach us at BAE or UKY BAEinfo@gmail.com. On Carla and my behalf, want to thank you guys for, tinkering with us today. And we hope you enjoy the rest of your E-Day. Bye, guys.
Bye.